Good. Got a little one, so that always changes things. All right, guys. Let's talk about what we're going to do today. Basically, synopsis is we're going to continue from where you left off on your unknowns. I thought of this strategy today. I mean, I've told you, I think you should do the aqueous solubilities at least 2 to 3 times. A nice strategy actually might be first thing today, redo it. That way you put some distance in between. You know what I mean? You can kind of come at it with a fresh sort of perspective about it and really convince yourself that you got the solubility test that you think you did. Probably next week, maybe. I'll have to look at the schedule again, but probably next week I'll start meeting with you guys on a one-on-one basis and just kind of talk about like what data you found. I'm not going to say, oh, you should have gotten a positive DMP test. Why didn't you? I'm not going to say stuff like that, but I'm going to like kind of probe your thinking and stuff and make sure you don't get too far off the trail into the woods. Okay. And then, so I would make sure you get your aqueous solubility done. And then you make sure you've done the chloroform solubility. The chloroform solubility, I don't think you have to repeat. I think that's pretty, black and white. And then we're going to be taking an NMR. You're going to get an NMR of your unknown. And by the way, I thought I had printed them out, but I hadn't. But I have a document that's like it's kind of a cheat sheet for doing the procedures, so that you don't have to follow the procedures exactly. The book procedures, they're a little bit long, so they can kind of slow you down. And so I have a handout that tells you how to do each procedure nice and quick. And included in that actually is how you do the, how you prepare your NMR sample. We prepare the NMR samples pretty concentrated, and that's so that we can acquire a C13 quickly. Okay, C13 isn't nearly as sensitive as proton NMR, and so you need more material or you need more time. We don't want to take more time, so we put in more material. And get started on IR. Hopefully you had a chance to look at the video on running the IRs. I put that out right before spring break because that wasn't the best time to do that. But it's on YouTube. It's there. It never goes away. So, and then we're gonna add on a couple of qualitative tests today. Okay, I'm gonna go over the 2,4-DMP test. I'm gonna go over the iodoform test. I'm gonna go over the Tollens test, the bicarbonate test. I think that's it. And again, just because I talk about them today and we draw out the mechanism and everything like that, don't feel compelled like, oh, I got to do that test on my unknowns. Okay, do that test on your unknowns if the data suggests that you might have that function. I think that that's in the realm of possibilities. Okay. Okay. So, stuff on the board.
Aqueous, particularly, solubility test.
Probably redo them.
Chloroform 2. Okay, don't need to redo that one. Have a procedure. Synopsis handout. Okay, and this you're going to actually hang on to this, hold on to it very carefully. You're going to return this at the end. Today we are doing one NMR. CL3 samples only. Okay.
So if your unknown is soluble in CHCl3, regular chloroform, then you know it's going to be soluble in deuterated chloroform. They have the same solubility profile. If your unknown wasn't soluble in deuterated chloroform, then we're not going to do it today. We're going to, when you switch back and forth solvents, that can throw the shimming off a little bit on the NMR, so we'll get cleaner spectra for everybody if we just try to keep it pretty standard on which ones we're doing. I think none of you should have two unknowns that are insoluble in chloroform. You might have one, but I don't think anybody should have two. Let me know if that's a problem. And started on IR today. Finish up on melting points, and I think later on today I will probably show you, explain how you do the boiling point as well, so you can do that if your stuff is liquid at room temperature. Okay. Qualitative tests. Do standards. Remember, if you should do the standards right alongside. Okay, so the first one, the DMP test is for aldehydes and ketones, right? We have an aldehyde standard, we have a ketone standard. So you can, I think the standards are in hood too. So you do it right alongside, so that you have an idea of what a positive test looks like. Okay. If you come up and ask me, hey, is this a good positive DMP test? I'll say, oh, let me see the standard. So have that be. Okay. All right. So. So this is for alds and ketones. Okay. This test, some of the tests we're going to learn they're a little bit wishy-washy. And you're like, it's not a positive test, I don't know, it's kind of subtle. DMP test, 99% of the time, it's real dramatic. It's like, boom, okay? You get precipitate, and it's usually has some color to the precipitate. I'll talk a little bit about the color. Okay? But the main thing is you get precipitate, and it tends to be pretty dramatic. Oh. Generally, very reliable and dramatic. Okay. All right. So how does it work? All right. Let's say we've got this guy. I'll leave it generic, and that way I can be ketone or aldehyde. The reagent, 2,4-dinitro phenylhydrazine. Okay. And then you need an acid catalyst, which is already mixed in with the DMP solution. Reaction. Okay. I don't know if I have ever said this to you guys or not, but if you have an acid or a base as part of your reagents and stuff, that's usually the first step of the mechanism. The acid-base stuff usually happens
solution, your carbonyl. Okay. That makes this already partially positive carbonyl carbon very partially positive. Okay. And this, and hydrazines behave a lot like primary nitrogens do, but primary nitrogens are very good nucleophiles. Hydrazines are actually even better than primary amines. Partially positive charge on that carbon there attracts the lone pair of that nitrogen. Proton is going to fall off this nitrogen here, right? And proton is going to be put on to that oxygen there in the next step. Okay, that's always the place that say it's the one shortcut that's allowable. Rather than showing two individual steps, come off, come on, we'll just right. Proton transfer. Describe this as a sort of anchored water, all right? Water that is anchored onto the molecule, and thus if it leaves, it's neutral water leaving, so it's an excellent leaving group. We could do so in sort of a push-pull fashion. These electrons come down, those electrons go onto oxygen. Draw on the final product for you. But I will here in a second. Okay. We are actually there. All we have to do is get rid of that proton there. And hard to say what that would be. There's a number of different things. It could be water, it could be one of these other nitrogens. There's lots of nitrogens in this solution. So we'll just write B lone pair there. Grab that proton, those electrons go back there. And we have our final product. Move this nature. Remember that guy can spin around. And so this is a hydrazine. Okay. And when it essentially this is called a condensation reaction. When it condenses with a carbonyl, okay, makes that the primary nitrogen of the hydrazine makes that carbonyl-looking like thing with the carbonyl carbon. Okay, when you get this double bond here, that's called a hydrazone. Okay. All right. Cool. Fun mechanism. A couple little details. emphasize the sometimes. Color can be informative. Okay, I wouldn't put a lot of stock into this. I can't remember if I said this in this section or not, but in general, what I always tell people is that if all the evidence is sort of leading one way, but you've got one piece of evidence that's leading you a different direction, majority rules. Go with what the majority says, except NMR. Okay, NMR don't lie. All right. If you think you have a ketone, then the C13 better have a carbonyl peak somewhere around 190 to 200. Okay. All right. But you know, this could be confirmation. You can suspect your level of conjugation here, and this could be confirmed. All right. So how can the color be informative? If it's not very conjugated, okay, so that's an example of an unconjugated carbonyl. There's no you know, double bond that's nearby or something like that. Right? Those tend to be more yellow. Okay. If it is conjugated, okay, just kind of regular amount, then it tends to be orange, red. And if it is very conjugated, okay, that's not, this is very, then it's even more red. Okay. Okay. Now, this is for aldehydes or ketones. Okay. So, if it's a positive test, that's all you know. You know that you have an aldehyde or a ketone. You don't know, you know, which. Right? And so, if you get a positive test, you should do the Tollens test, and you should do the iodoform test. Okay. If this is positive, you should do both. If this is the Tollens is for aldehydes and the iodoform is for methyl ketones. If this is negative, there's no reason to do the Tollens or the iodoform test. Okay, you already know you don't have an aldehyde or a ketone. Okay. All right. So. But before I get to that, actually, if it's initially negative, okay, this is probably in the synopsis cheat sheet note. Put in a water bath. That should be a warm water bath for 15 minutes, just to make sure. I feel like in all the unknowns, you know, that we sometimes assign to students, I feel like there's one that is hard to get the reaction to go. There's only one, if memory serves. Okay, but a little heat can always, can often help the reaction go on. All right. Note. If positive test, okay, do Tollens and iodoform. Okay. Negative test, don't do Tollens, Tollens and iodoform. Okay. All right, beautiful. Oh, let's see if I can squeeze in iodoform here. All right. If you have a methyl ketone, which means one of your, you have an R, right? And then, purple. So that's a CH3. I just wanted to draw one of the protons extended out for the purposes of this method. Okay. You need hydroxide and you need elemental iodine. Okay. What you end up getting is you actually cleave that carbon-to-carbon bond. Cleaving carbon-to-carbon bonds is tricky. But under these conditions, you can do it. You cleave it, and you actually convert this into a carboxylic acid, okay, which is immediately deprotonated because it's in a basic environment. You get a carboxylate, and then you get iodoform. That's chloroform. Iodoform is just the iodine version of chloroform. Okay? And this is what precipitates. You get a yellow precipitate. This is a little bit subtle, this test, okay? So very important that you do that you do a standard. I think the standard back there is acetophenone. Okay. All right, so how the heck does this happen? Well, got an acid or base. That's probably the first step. Okay. So, deprotonates. Actually, I'll show you the more classic way. So we're going to put an anion on an alpha carbon. Remember, alpha is a carbon that is adjacent, connected to a carbonyl carbon. That's an alpha carbon. And we're going to put a negative charge on there. Part of the reason why this is, somewhat readily taken off with hydroxide, okay, is the fact that the conjugate base is stabilized by resonance. Okay? And in fact, the other resonance form is the one that we predominantly show with enolates. What the heck is what I'm talking about? Okay, that's an enolate form. All right? The other resonance structure has the negative charge right on that carbon. We've seen a couple of cases where elemental halogens can act as electrophiles. Okay? And this is such a case. Electrons come down here. Those electrons go out there. Okay. And what you've done there is you have added. You have added an iodine to the alpha position. Okay. So you've added one atom iodine there. I'm going to again extend out. So now what you have here is you've replaced one of these hydrogens, one of these three hydrogens, with an iodine. You have two left. I'm extending one out again. Okay? Hydroxide does it again. I'm going to draw the other form of the resonance structure. Okay, so we've got C, H, there's an iodine there. Okay. And
now the negative charge, I'm showing the resonance structure with the negative charge is on the carbon there. Okay. So out of curiosity, do you guys think this proton was easier or harder to remove than that proton? Which one is more acidic? The original methyl ketone or this iodo methyl ketone? Which one's more acidic? When you're trying to compare acidity, what do you always do? What's the standard? This is how I make that decision. You compare the conjugate bases. You decide which one of the conjugate bases is more stable. Okay? And if it has a conjugate base that's more stable, then the proton originally was easier to take off with more stable. So that means, is this conjugate base more stable, or is that conjugate? I know they're different resonance structures, so it makes it a little confusing. But you know, they both have the same, the other resonance structure. Okay. So which one do you think is more stable, this one or that one? This one. Very good. That's true. Now why?
Well, 50-50 shot this test.
So an iodine is more electronegative than a hydrogen. Okay? So that can help actually alleviate some of that negative charge on it. Okay? It's also very polarizable, as we know. It's ginormous. It's the Jupiter of atoms. Okay? And so it can also help take on some of the excess electron density that's sitting on that particle. That makes sense? That's going to come into play here in another second, in another context. All right. So, we've got another molecule of iodine. And it happens again. And so, just getting okay. Now two of the hydrogens have been replaced. Is this proton going to be easier or harder to take off than the earlier two? Is that proton harder or easier than that proton to take off? Is this more acidic than that? Yes, yes. For the same reason that we just talked about comparing the first two. Okay? Now the negative charge that's going to end up on this carbon is stabilized by two ions. Okay? All right, so hydroxide, little itty bitty hydroxide here. Grab this proton. Okay. Let's do this resonance structure again. That's the most common way of showing enolates. Okay. All right. There's no more protons on here to take off. Right? What hydroxide can do now is hydroxide can behave like a base or a nucleophile. To this point, it's been behaving like a base, okay? But it can also act as a nucleophile. We know that carbonyl carbons are susceptible to nucleophiles because of that partial positive charge on that carbon there. Okay? So hydroxide will come in here, attack that carbon. Okay? It creates what we call a tetrahedral intermediate. Tetrahedral